Hey everybody, today we're going to take one last look at higher order derivatives, just keeping it slow this week. And just another look at two more word problems, different starting points, maybe different ending points, and then just so you guys could get another sense of the style of question. So today, first thing, let's take another look at velocity and acceleration. And more specifically, this first question, we're going to look at how do we find the acceleration on the moon if we're given a function that models the behavior of a rock being thrown on the moon and how it falls to the surface. So in this first question, you see that we have an astronaut that's standing on the surface of the moon. He throws a rock into the air. The height, s, in feet, of the rock is given by this function. S of t is equal to negative 27 over 10 t squared plus 27t plus 6, where t is measured in seconds. And what we're going to do is compare the acceleration due to gravity on the moon compared with the acceleration of gravity on Earth, which we've seen has been negative 32 feet per second squared from our previous days of work. So let's start by finding the acceleration. Now, we know acceleration is the second derivative of our position function. So we're going to start just by finding our first derivative. So we're going to have to find s prime of t, which we also know is the velocity function, so v of t. So in this case, we're going to end up with negative 54 over 10 t plus 27, and then the 6 goes away. Now we could also rewrite this in simpler terms. This was really just the same as negative 27 over 5t plus 27. We could reduce that negative 54 over 10. Then if we want to find our acceleration function, we just take the derivative one more time, right? In this case, it's the second derivative of our original position function, or the first derivative of our velocity function, which gets us that acceleration function. And in this case, that negative 27 over 5t just becomes negative 27 over 5. So remember, gravity is just that constant acceleration being pulled down, so this makes sense that there's no t. So what we're really finding out is that the acceleration on the moon is negative 27 over 5 feet per second squared, which really, if we were to round this number, right, with the Earth, we knew that it was negative 32 feet per second. If we divided this, we would end up with negative 5.4 feet per second squared as our acceleration. So it's a much slower acceleration due to gravity, which also is why there's less gravity. So let's continue on and see what happens when we're not necessarily starting with the position function anymore, but in this case, starting with the velocity function. So the question states the velocity v in feet per second of a certain automobile starting from rest is v of t given by 80t over t plus 5, where t is the time in seconds. What we want to do is find the velocity and acceleration of the car at 0 and 10 seconds at those points in times. So first thing we need to do is identify our velocity function and identify our acceleration function. So we know, let's start with our velocity. We know they gave this one to us, is that the velocity is equal to 80t over t plus 5. So if we want to find our velocity at 0 seconds and 10 seconds, we just have to substitute those values in for t. So we have to find the velocity at 0, which is 0, right? It makes sense. It's at rest at that point in time, so it's not moving at all, right? And that's the velocity in feet per second. If we want to then also find the velocity at 10, we're just going to substitute the 10 into that equation, and we end up with 53.5. So 53.5 feet per second. Now, the question also asks us to be finding the acceleration at both 0 and 10 seconds. So we know that if we have velocity, all we have to do is take the derivative of our acceleration function, of our velocity function, to find that acceleration function. Now, in this case, we have a fraction that we can't really rewrite very well, or we can't simplify, or we can't necessarily just divide evenly. You could make that t plus 5 to the negative first power and use the chain rule, but I'm just going to keep it with the quotient rule here, and just do our low, right? Take our low function, which is t plus 5, times the derivative of our high function, 80, minus the high function, 80t, times the derivative of our low function, which is just 1, so you don't really have to have that in there. And then that is all over the low function being squared t plus 5 squared. And then we just need to substitute in and find those values. Now you guys have a choice here. You could take your you could type that into your calculator, put it in y1, do a substitution. You guys could do STO. Or in all honesty, if you wanted, you could type our original function in, that velocity, and use nderive on the calculator. So your choice. But when you do that, you should end up with that the acceleration at 0 is 16 feet per second squared. And at 10 seconds, the acceleration is 1.78, right? 1.78 feet per second squared. That's all for today. 2 examples just like you guys see here for you to practice tonight. And that's all going to be the new stuff for the week. I'll have some little extra practice for you guys on Thursday. Hope all is well. See you guys. Talk to you guys soon.